Amazon Prime Air, and so he focuses on both, applied and fundamental problems related to fluid dynamics and turbulence. And his research area focuses on, he covers a wide range of areas, for example, wind engineering, infrastructure resilience, and environmental engineering as well. And his group, like his current group at Columbia University, collaborates with governmental agencies, industry partners, that address complex engineering and geoscience challenges. So with that, I would like to welcome Dr. Giometto for his talk.
Thanks, Fayez. Well, thanks everyone for being here today. It's really a pleasure to be talking about some of our ongoing research on hurricane boundary layer turbulence in such a prestigious institution for wind research. So this is work that is being started with Mostafa Momen, who was a postdoc in my group when I started the tenure track. So the advice for every tenure track is get a postdoc in your year one. They'll set you up for success. Mostafa did some of the work, and then more recently we got a grant from the National Institute for Standards and Technology to go a bit further, and we hired Kishore Satya, who's been a really terrific PhD student and has really pushed a lot of this research. So a lot of the credit here goes to the student, not to me. Yeah, before delving deep into the presentation, this is my research group when it was at its peak in terms of at least number of students. There were some PhD, postdocs, research scientists, some research engineer, a couple of undergrads. We are mostly a computational fluid dynamics group, so we develop our own software, put a lot of pride in the software we develop, and then we use it to gain insight on a range of problems. It typically depends on what kind of funding we manage to get. But mostly around urban micrometeorology, flowing polar regions. 2 years ago, went to Antarctica also thanks to this project, so I was very happy with that polar program from National Science Foundation. National Institute of Standard and Technology, we got to study tropical cyclone turbulence, which is what I'm going to talk about today. And more recently, we also got some funding from the Navy to study air-sea interaction, and I discovered that's such a difficult problem, and so if you can stay away from it, it's not bad. We've been working for industry for a while, like Fayez said. We've been working for the Amazon Prime Air program, their delivery drone program. The drone couldn't withstand wind near buildings, and then they realized, okay, we need some CFD support, and from there, we made them realize weather is also quite important for operations, and so it's been a very long and fruitful collaboration. They've been funding some research in my group too at Columbia. We've gotten quite lucky with funding. We got funding from the Department of Defense, mostly Army and Navy, National Institute of Standard and Technologies, some from NSF, and some from industry. All right. So motivation for researching for fluid dynamics research in hurricanes, probably you don't need that much of an introduction, but as you know, we study this flow phenomena because they're the most violent type of storms on Earth. On average, we have 6 hurricanes in the US each year, and these hurricanes are predicted to become more intense and destructive due to increases in sea surface temperature. So as engineers, we really should gain a better understanding of how they form and their properties. So hurricanes, they typically form in warm waters, and they can go by many names depending on where they happen. In the North Atlantic and Northeast Pacific, we call them hurricanes. In the West Pacific, they go by the name of typhoons. This is China, Philippines, Japan, and in the Indian Ocean, they go by the name of, and Southern Ocean, they go by the name of cyclones, but they're pretty much all the same physical phenomena. From a fluid dynamics perspective, a hurricane does not arise as an amplification of a linear small amplitude perturbation. They typically grow from a linear interaction from a pre-existing storm. So you typically need a number of ingredients for a hurricane to form. Pre-existing low-level disturbance with a low-pressure core, sufficiently warm sea surface temperature, typically at least 26 degrees, unstably stratified atmosphere, high humidity in the lower middle levels of the troposphere, and then low vertical shear, because otherwise they would just get sheared away. If all of these are present, then chances are you get a hurricane, or maybe not. Now hurricanes, the structure of a hurricane and their mechanism sustaining hurricane can be compared with the Carnot heat engine. This was initially proposed by Kerry Emanuel and has since received a lot of attention. So let's see what is keeping an hurricane spinning. So from the warm ocean, you have latent and sensible heat warming the atmosphere. Because you have a low pressure core, you typically tend to get particles spiraling inward near the surface. These, they receive heat from the ocean, and they reach the core, being a bit warmer than the surrounding environment, so they're positively buoyant, and they start ascending through a process that we call convection. And at a certain point, water vapor condenses, you have releases of latent heat, and these essentially warms up the core, contributes to lowering the pressure, and strengthen the gradient between the pressure at the core and the pressure outside, so it strengthens the pressure gradient. From a dynamics perspective, this pressure gradient is balanced by centrifugal acceleration, so that's how essentially strengthening of the low pressure core from these thermodynamic processes strengthen also the rotation. Then as the particles reach the top of the tropopause, then they tend to lose heat through radiative cooling, and then they'll fall back to restart the cycle. This is at the most idealized case. Now, how do we model hurricanes? How do we get inside of hurricanes? The most common approach is through mesoscale simulations, like the one you're seeing here. These are simulations that can resolve the entire hurricane. Think of the radius here can be thousands of kilometers. These are pretty big simulation. And they feature grid resolutions in the horizontal directions that are approximately 1 kilometer. Because the grid resolution is 1 kilometer in the horizontal direction, you cannot really use this type of simulations if you want to gain insight on boundary layer turbulence. Boundary layer, for those of you that are not familiar, is the lower portion of the atmosphere, the one in direct contact with the surface. It's in a state of turbulent flow, and it's typically 1 to 3 kilometers thickness, so it's very shallow. So your resolution, horizontal resolution, is 1 kilometer. Certainly you cannot resolve eddies within that shallow region. And this is really what this project sponsored by the National Institute of Standard Technology is about, trying to bridge that gap and develop a framework that allows us to study hurricane turbulence. This is an outline of the presentation. So I'll first present a numerical framework that we've developed to simulate turbulence in the hurricane at very high resolution. I'll then present a database that we generate with this framework, and then do some physics analysis and propose an analytic solution that describes mean profiles away from the wall, and then I'll conclude. All right, so loosely speaking, a hurricane can be conceptualized as an axisymmetric spinning eddy. Here, it's a top view of the velocity magnitude in a hurricane. Yellow means slow and red means faster. So you see the hurricane at the center has the so-called eye. This is a region with low pressure, very quiescent flow, low wind speed. This is bounded by what was called the eye wall. This is where the highest tangential wind speeds are present. And then you have the tangential velocities decaying as you move farther away from the axis of rotation. The size of the hurricane, in this case, we had the order of 1,000 kilometers. Here you have a vertical cross-section through the same flow field. So you see this is the eye wall, and what I want to point out is that these isolines denote regions of constant radial velocity. So you see, because the isoline tend to concentrate towards the wall, we have a gradient of radial velocity in the radial direction. And I'm pointing out, essentially, there are large-scale gradients of tangential and radial velocities. And these, as we'll see, it's one of the challenges we have to cope with. So within the spinning eddy, if you want to simulate these at, say, 10-meter resolution, it's really hard because you see it's 1,000 kilometers in size. This is kind of the large outer scale. And you want to go down to 10-meter resolution. It's too much to cope with from a numerical perspective. So what we did is we built on an idea of George Bryan, a tank car, and the idea consists essentially of simulating only a small portion of the hurricane, and accounting for the effects of larger scale dynamics, those large scale gradients, for example, and centrifugal accelerations within this small domain. If you can do that, then you can perform a simulation at crazy high resolution because the extent you're simulating is very small. Now, the type of simulations we would like to run look pretty much like this. This is a simulation, largely simulation in a so-called open channel flow setup. The open channel flow setup is very convenient from a numerical perspective. The way it works is you typically drive the flow with an imposed geostrophic or applied pressure gradient. You can stratify the flow by applying a temperature boundary conditions, for example, at the lower surface. At the top, we have an impermeability condition, so flow doesn't go through, and free lead, so the flow can flow past in parallel to the top plane freely without having any stress. And this is the important part. Horizontally, we apply doubly periodic boundary conditions, so the flow that goes out comes in. This is very, very convenient from a numerical perspective because it means I don't need to prescribe an inflow. And in large eddy simulation, the inflow is instantaneous, it evolves, so it's really, really hard to prescribe. However, the problem is that, as we saw in a hurricane, if you want to simulate that small portion, the hurricane has large-scale radial gradients. Those, because they're radial gradients, they are non-periodic by definition. So that complicates the use of this very easy and fundamental type of numerical setup. And in the slide that followed, I want to show you how basically we address these in a way that starts from the governing equations. This is how our research has changed a bit to compare with the innovation we proposed compared to the previous work that is we derive the governing equation straight from the Navier-Stokes. So we start from the Navier-Stokes equation. These slides will have a lot of math, but you don't need to follow everything. So we start from the Navier-Stokes in Cartesian coordinate, where XYZ is the radial, tangential, and vertical. UVW, the corresponding velocity, P is pressure, rho is constant density, F, the Coriolis acceleration, and this is the stress divergence, which can be viscous if you run in Navier-Stokes, DNS, so with the Navier-Stokes, or it could be the divergence of a subgrid scale stress tensor if you're doing large eddy simulation. Okay, so momentum for U, V, and W. Radial, tangential, and vertical. Now we do a triple decomposition of the velocity, and this is really the key step, where we say, okay, our velocity UI hat is a space and time average component plus a departure of a time average from the spatial mean plus a fluctuation. Then we assume that the spatial and time mean is much larger than the time variation from that space mean. So you can imagine if you have a wind speed of 50 meters per second, and in the radial direction is changing between 52 and 54, maybe within your domain, this is a good assumption. With this assumption and these, we plug this back in, leverage this assumption, we get this new set of equations, where now the U, V, and W, or this UI, is just the time and spatial mean plus a fluctuation. So you see just this one plus that one. The effect of this temporal departure from the spatial mean, which is the aperiodic component, now we basically include it in the equation as additional terms. So you see we've dumped the non-periodic term inside the governing equations. Now we need to model those terms. To model those terms, we take the Navier-Stokes in cylindrical coordinates and we look how those terms would look like. So we have the radial gradient of the tangential time mean, time average velocity. These, we model it as a power law of R. So if you model it as a power law of R and proportional to Vg, this is what you will get. The gradient of time average radial velocity with respect to R, you get it from continuity equation. Because you have this is 0, then you can get this. This is an assumption we make that the radial gradient of the vertical time average velocity is 0, so we assume no subsidence, which is okay if you're away from the eye wall. If you're near the eye wall, then you actually get subsidence, so this constrains us to operate with this model away from the eye wall. And the radial pressure gradient, time mean pressure gradient, which is a term in the equation, we set it equal to basically we set it in a so-called gradient twin balance, so it's equal to the Coriolis acceleration plus centrifugal forces with Vg within the gradient twin. The problem is axis symmetry, so all the gradients with theta are 0. Now, we're simulating a domain that's very far from the axis of rotation and it's kind of small. So the change in the theta angle is quite small within that domain. And also R is large. R is the distance from the axis of rotation where our small domain is. So then we can make also this assumption: cosine of theta is 1, sine of theta is 0, and the small r coordinate is more or less the value of r at the center of our domain. And if you then map this back into the Cartesian coordinate, you get an expression for these various large-scale average, time average terms. So this is basically starting from the Navier-Stokes in Cartesian, looking at what would happen if we had terms that were aperiodic in R, then looking at Navier-Stokes in cylindrical coordinate and mapping a value to those terms in order to get some expressions that are compatible with radial gradients in the tangential and the radial velocity. So essentially, we pay a price in the sense we go from a polar coordinate to a Cartesian one, but because we're far from the center of rotation, that we found it's pretty okay. Now, you can forget everything if you didn't like the mathematical part, but this is what we get after all that derivation, which took a very long time. We get a set of equations for U, V, and W, where the black terms are the usual Ekman layer equation that you would run if you wanted to perform an Ekman layer simulation, plus now some blue terms that are approximation of those terms we had just derived from going into polar coordinate and then transforming into Cartesian. Now these are mostly centrifugal acceleration terms and dynamics that are introduced by the gradients of those large-scale time average velocities. See this, it's always a v squared over r, except this, well, also this term. So now, if we resolve these equations for my u, v, and w, where the u, v, and w are periodic within a channel flow located at the distance r from the axis of rotation, along with the thermal energy and continuity equation, where we assume the flow is incompressible. Now what we'll get are dynamics in that small channel that are more akin to hurricane turbulence than they are to Ekman layer turbulence, because we have some acceleration terms. One downside of this system of equation is that we have a lot of input parameters. You need to prescribe the gradient wind magnitude and its vertical gradient, the Coriolis frequency, the parameter n with the term which is the exponent of the power law of the tangential velocity gradient in the radial direction, r, z0, the Lagrange roughness length, and n, which is the background stratification. So the first thing we did with this algorithm is we ran some simulations and compared against experiments to verify whether some of the assumptions we made in there are valid. So we leveraged a pre-existing large eddy simulation solver. We modified it to account for those additional terms. This is a channel flow with an aspect ratio between the x and the y of 1. So this, and between the x and the vertical and y vertical of 2 pi. So if the vertical is h, the horizontal is 2 pi h. This is a kind of a custom domain size in standard channel flow turbulence. Reynolds number, we assume it's infinity. We have a mix pseudo-spectral and finite differences solver, so Fourier basis functions in the horizontal and second order fully staggered in the vertical, Adam-Bashforth scheme, second order, and fractional step magnitude velocity and pressure coupling. These are just some details. This is the grid resolution we adopted, so it's a pretty large RAM, but not crazy. This type of software runs, say, 100 times faster than OpenFOAM you would expect, more or less, and it's much more accurate. So this is somehow a software that's developed to study precisely this problem. It's very useful to do that because then you save the compute cost later. We use a Lagrange scale dependence Magorinsky model for closing the equations. We compare against measurements over the Atlantic Ocean. These are composite measurements, and one case over land, in this case from radar data in Miami, and just in terms of mean velocity profiles here. And you see, so the blue and red are the tangential time average velocity from the measurements and the radial time average velocity from the measurements. The gray and black lines are from the large eddy simulation algorithm we've developed. And you see we're doing a pretty good job once you prescribe the right parameters. Some of these parameters we tuned, such as the n. Other parameters, and these is 0. Other parameters, we had them available from the measurements, so we just prescribed them. When you have a lot of parameters, you know that you can play a bit around and then you can get good matching, but we were really satisfied with these. So With this, we got the paper out. We also validated in terms of second-order statistics, momentum fluxes, yeah, we consider the code validated. One thing we did now with the validated code is to look at what the impact of those blue terms in the equation is on the structure of turbulence. So what we did to enable that is we performed simulations with the blue terms and simulations without. And then we looked at the instantaneous snapshot over a horizontal plane of the velocity magnitude. This is what you see without those terms. This is what you see with those terms at a height of 438 meters above the ground. This is a height where centrifugal forces are playing an important role. So that's what we wanted to do. We wanted to see where centrifugal forces play a role, what turbulence is going to look like. The above is a isocontour of the two-point correlations. This is telling you how correlatedly spaced the flow is. So what we see here is basically, if you're running simulations without those blue terms, those hurricane-specific terms, turbulence is the familiar one where you have streamwise elongated high and low speed bulges that alternate in the cross-stream direction and that approximately align with the mean flow, this black arrow. Once you add those terms and centrifugal forces start to play a game, now what you see is essentially that these coherent structures become a lot more scrambled and also misaligned with respect to the mean flow direction. And the reason for that, so the flow becomes a lot less coherent, and the reason for that, if you want to look at it from a mechanistic perspective, is as follows. So this picture, we're looking at the mean flow direction is denoted by this arrow. The vectors denote the departure from the background flow. So, and the red means fast, blue means slow fluid. So you see, if you have a region that's relatively faster, because there are centrifugal accelerations, this region is going to experience a very strong push outward, because the centrifugal acceleration will be higher. So you get from these, if you're looking at radial times tangential velocity fluctuation, they're both larger than 0 in this case, so you get a positive U prime, V prime flux contribution. This is a turbulent flux of momentum within the plane. If you have a region that's slightly slower, you get the opposite effect, of course, so it's going to move into with respect to the mean flow. And this, as a matter of fact, it's another positive contribution to the U prime, V prime flux. So adding those centrifugal forces basically enhances significantly the flux within the plane by causing this mixing. And what we observe, in fact, in this hurricane simulation is that the in-plane flux is much, much larger. So in the HBL, so the hurricane boundary layer, this flux is much larger than in a comparable ABL, or atmospheric boundary layer. So this was one of the findings. Then Mustafa got a job at the University of Houston, left, and this for a year I wanted to do new things, but I could not. Until then, we decided to write a grant. The grant was successful, and we hired Kishore. So Kishore, for the first year of his PhD, essentially what he did is try to understand what Mustafa had done and reproduce it, and then go through the courses, which, as you know, it can be a bit painful in PhD life. But then in year 2, what we decided to do is to leverage that framework. We made it a bit faster and a bit more consistent. And we decided to build a database of hurricane simulations. And we could do that because this solver is really, really fast. What we did is we consider 3 values of the gradient wind, 30, 45, 60 meters per second. 2 values of its vertical gradient. This is a gradient with respect to the vertical direction of the gradient wind. 2 values for the n parameter. 3 values for the aerodynamic roughness length from, say, smooth oceans to small obstacles over land. 2 values of the Coriolis frequency from San Juan to New York, and 3 values of the radius. The radius, as you might recall, is the distance at which we center that small domain from the axis of rotation. These corresponded to 216 simulations in total. They ran for about a year or so and burned, I think it was 150,000 core hours, 150 million core hours. So if you know the cost of core hours from high performance computing, it costed a lot. But then the final results we were really, really satisfied. Actually, we had to run multiple times because there were some mistakes in the first run. So, but then we got these very beautiful smooth profiles for, in this case, this is tangential velocity and not tangential and radial velocity, tangential and radial velocity. In this case, we kept all the parameters fixed except r, and here we kept parameters fixed except z0. So we can start basically doing an exploratory data analysis and try to understand, okay, what happens if we increase the radius from 40 to 120? Well, we see that the jet tends to thicken, the boundary layer tends to thicken, and the height of the jet increases. The effect of Z0 is similar. Now you get a stronger also increase in the radial wind speed. And you can go on for a year if you want, because in a dimensional world, this problem has so many parameters that you're never going to be able to really fully grasp it, because you change something, keeping something else fixed, then you need to see if you change that something else, if that thing still holds. So once we figured that out, the first thing we did is to say, okay, let's take a step back and use a more boundary layer meteorology approach. Let's identify how the problem scales in the outer layer, so away from the surface, and in the inner layer. Now, in the outer layer, a very important parameter is the so-called hurricane boundary layer height. These can be identified by looking at the radial velocity profile, this mean velocity profile, and picking the first zero crossing of that profile. That defines the hurricane boundary layer height. It's just one of the ways in which you can do that. This parameter enters dynamical models of the hurricane boundary layer as well as wind engineering profiles, as you can find in Dickery et al. So it's really a key parameter that allows you to scale profiles away from the wall. So what we did is we derived the scaling for this quantity, and I want to take you through the approach that we used in the next slides. This is based or follows an approach that was initially proposed by Pollard et al. In the 70s, which proposed a scaling that reads friction velocity divided by square root of Fn for the deepening of the upper ocean mix layer under a range of conditions. So I'm going to take you through the derivation because it's very simple and I think it's quite illuminating. So we start from the equations for the radial and tangential velocity. These are the material derivatives, the Coriolis and centrifugal acceleration term and stress divergence. These have been averaged over the horizontal, so imagine these are just profiles of U and V. Next, we call these alpha and these beta. These are two parameters that will appear. Next, we depth integrate this equation and rewrite the equation for that average quantity. So now, see, if we depth integrate the UDT, you can rewrite it as the mean of the UDT over the height times the height. Similarly, you can rewrite this term as follows, and the right-hand side is a gradient in Z, so we just get the value of the stress at the top and at the bottom for the radial and the tangential velocity. Now, we need a model for the stresses at the top and bottom because those are unclosed terms. What we assume is that in the radial direction, the stress is zero since most of the velocity is in the tangential direction, and we use a quadratic drag law to model the bottom stress in the tangential direction. So this is our parameterization for the stress at the surface. Now we need a parameterization for the stress at the top. And here, what we assume is that the stress at the top is due to the added momentum from entrainment. In other words, as the height of the hurricane boundary layer, this h, changes in time, the boundary layer has to entrain momentum, and this can be written as the product of a velocity difference, where one velocity is the velocity above the boundary layer, and the other is the average velocity of the boundary layer times the rate of growth of the boundary layer. This essentially, it's mapping the velocity that you have and the rate of growth of the boundary layer to stresses that contribute to that growth. We do that for the radial and we do that for the tangential velocity. All right, now we parameterize this term. We can substitute these expressions into the previous equations and get the following. Now, these are equations for h u bar and h v minus vg. So these are our two variables now. So we can solve them and get this expression. So h times the mean, that average mean of u is proportional to a prefactor, 1 minus cosine of it, where I is a parameter. And same for h times v minus vg. Now, if we want the goal here is to find the model for h. We want the height of the hurricane boundary layer. Here we have two equations, but h, u, and v as unknown. So 2 equations, 3 unknown. We need an additional equation. So what we assumed is that where the boundary layer ends, buoyancy destruction is going to be of the same order of magnitude of shear production. So we use a Richardson number criterion. The Richardson number is buoyancy production or distraction over shear production. You can write it using K-theory as follows, and you can essentially express it now as a function of the Bruba-Sala frequency, which is an input parameter in our model, the net average velocity, and the height of the boundary layer. This is like the mean shear. And we say, where this is equal to 1, that's where the boundary layer ends. You have a lot of flexibility. You can pick another number. If you prefer 1, work very well for us. Now, we substitute this equation into the previous ones. You sum the other two, you will find that basically the sum has a term that reads as follows, so you can get this equation here. This is an equation for just h. You see, h is equal to something cosine of it plus sine of it. Now, this argument here, sorry, this is a function here, will become the largest for it equal to pi. So we say, okay, when it reaches pi, the boundary layer stops growing. That's where the height of the hurricane boundary layer is defined. If you do that, and then you compute an expression for h, we get that h is equal to a prefactor cs times the friction velocity divided by square root of beta n, where beta is basically this term here. In the derivation by Pollard, what he had found is the h, the height of the mixed layer in the ocean, is u star over fn. So here, you see we have f, but we also have some terms that come from those new terms in the hurricane boundary layer. So it's a very similar derivation overall. It's just that here we have new terms available. Now the beautiful thing is that if you pick CS to be 1.2 and we compare the hurricane boundary layer depth from the large eddy simulation and the one from this formula, we get this scaling, or this matching with an R square of 0.97. So at first I thought Kishore had cheated, and there's a lot of parameters, you can always get what you want. But yeah, I think he managed to convince me that actually it works really, really well. And this is because we have a stable stratification, and so the Richardson parameter criterion works very, very well. This was submitted to PNAS a couple of days ago. Let's see, usually if it makes it through the editor, then you have good chances. If not, we'll submit somewhere else. But we were very happy with this scaling. Now, if we go back to our sensitivity analysis, where we saw that the solution was varying quite a lot as we vary the parameters. These are the same plots as before. Now U is being scaled with G, V, we subtracted the gradient of the geostrophic wind and divided by G, and Z has been now normalized with the H that we found. And you see at the top, now we vary R, but at the top, very little variations. So we've collapsed basically profiles at the top. In both cases, here it varies to 0, you don't get a lot of variability. And this now allows us to better understand second order effects of variations in parameters, because we've collapsed the main scaling of the profiles. These are all 216 simulations, and this is how they look after we normalize with this outer scaling. So you see there is a little bit of variability here, but overall they all tend to follow the same approach. This is a very convenient framework for now gaining some more insight into the problem. Near the surface, the scaling it's a very trivial. So this dashed line is the log law. This lighter dashed line is the log law with a stability correction for stable stratification. The lines are the 3 simulations I had shown you before with R 40, 80, and 120, and keeping other parameters fixed. Z here is normalized with Z0, and U with U star. So very close to the wall, the velocity, the velocity magnitude follows the classical log law. This is very, very, very close to the wall. Now, if you account for stratification, you can actually get quite away from the surface with this simple log stability correction model. And then you have the jet, where instead the velocity then shows some variability with R, but near the wall you see we collapse everything with this simple Moninobuco stability correction function. So this was good news. If we looked at other quantities, so stresses, we found that from all the 216 simulations, they collapse very well with normalized with U star and H, and they follow so-and-so the new star profile. Turbulent kinetic energy shows quite some variability, not as much as if you were to look at it in a dimensional sense, but still a decent amount of variabilities. And colors are mostly variation Z0 and the geostrophic, the gradient with G. This is the eddy viscosity in dimensional form. You see there you have an order of magnitude variation between the two, all the simulations that we've run. This is what we get if we scale with outer unit with H and friction velocity. So now you still have some variability, significant variability, but we went from an order of magnitude variation to a factor of 2. Now we hope to be able to find a way to further collapse this, because this will allow us to then come up with a parameterization for T that we could use to resolve the problem analytically. Cool. So this is the first part of the talk, if you want, the database, large eddy simulations, and the scaling analysis. And we've got a few papers coming out from this analysis. But another work that I wanted to show you, talk about briefly, is a new analytical solution that we've derived for the hurricane boundary layer equations, which is valid under the assumption of constant eddy viscosity. So in traditional analytical methods, people have historically been depth integrating the governing equations and then applying some simplification and deriving an analytical solution for depth average quantities. And the solution of those analytical formulations typically depict horizontally average wind speed, vertically integrated and time average variations of the horizontal wind speed as a function of the radius, or vertical wind speed as a function of the radius. So you want to get an idea of how the flow is evolving in time and over horizontal directions. These are useful, but if you're in the wind engineering field, you also care a lot about the vertical structure of the wind, because if you have a low-level jet near the ground, it's different than if the velocity is a log-low type profile. So if we look at approaches that tackle the vertical variability of the flow, we found two main approaches. One, that it's purely analytical. You strip the equation off of all the nonlinearities. You assume and you get something like this. Then here you get the stress divergence. You use a K theory to close it, and you make the assumption of constant K. Then this has a classical trigonometric and K exponential function solution. And it has been discussed a lot, and it also matches pretty well with measurements under certain conditions. The other approach, it's a more empirical approach where measurements have been acquired, and now you fit profiles that you then use operationally. This is more accurate because you're fitting profiles that have been measured, and those profiles are somewhat informed by physics, but they might lack a bit of theoretical ground because they've not been derived as a solution of the underlying governing equations. So what we did as part of our work is we focused on the fully analytical approaches and tried to derive an extension of the solution that accounts for the nonlinear terms for a constant K. And in these slides, I'm going to talk a little bit about it, just to give you an idea of how we got there and how things look. So we made standard modeling assumptions. So we assumed that our gradient wind is a constant plus a linear function of height. We model radial variations. So these are the large-scale time average rate variations of the tangential velocity in the radial direction. We model it as a power law of R. These we get from continuity. Now we can rewrite the equations as follows if you do some normalizations, where psi now is a normalized z, v is v minus g, and u is the u. And we'll get 1, 2, 3 parameters, alpha, beta, gamma, which read as follows, where Rossby is a Rossby number of the flow, and n is our parameter. So these are all pre-computable a priori via your input parameters. Now, we seek a solution in terms of asymptotic series, And this is how we express the solution for u and v as a function of psi, where delta is a small parameter. If you substitute these into this equation, you get equations of different orders. At order 0, this is how things are going to look like. At order 1, this is how the equations look, and at order 2, this is how they look. The sum of solutions essentially will give you the total solution for the problem. Now, for the order 0 solution, the expression is as follows, and this was derived before by Keppert and other researchers. The order 1 solution that we derived is a very similar form. You see, it's still the order 0 plus decaying exponential and trigonometric function at higher frequencies. The order 2 solution, well, you see where things are getting, so we're not showing it, but we derived that too, and it looks quite ugly. But the nice thing is, if now we look, we compare the order 0, which is the one that was available before, against an exact numerical solution of the problem with constant anti-viscosity. So the exact numerical solution is in black. This is the radial component, this is the radial, and this is the tangential component. The order 0, you see, it's not capturing very well the modulation of the flow near the ground. Whereas if we apply our first order correction, now we're matching very, very good the exact numerical solution. Adding a second order correction brings you even closer. It's just that now you pay the price of having a very long formula, so at that point you might just as well just solve it numerically and forget about it. One useful thing when you have analytical solutions is that you can get expressions, analytical expression for variation of quantities of interest like the jet height or the jet wind speed. So in this case, what we found is that as the gradient wind increases, so as we increase g, typically you have the reduction of the jet height and the jet becomes more pronounced. As you can see here, this is within that constant anti-viscosity assumption. If we vary the radius r, now what we see is that we get the thickening of the jet, the nose of the jet is lifted, and because we have an analytic solution, we can also have an expression for the location of the peak for the u and the v velocity. So we can show that they scale like the square root of k r over g times a function of n, where k is the viscosity, r is the distance at which we center the domain, and g is the gradient width. This is very useful because now with a simple formula, knowing where your domain is, the geostrophic, the gradient wind magnitude, and the value of n, you can a priori, without solving anything, know more or less where the jet will be. And yeah, this takes me to the conclusion. So in summary, we've developed a largety simulation framework. We built a large database of numerical simulations. We analyzed it to look at outer layer and inner layer scaling of the problem. This is quite fluids type, fundamental fluids research. And propose an analytical solution for the mean profile for constant anti-viscosity. Looking forward, Kishore is still 2-3 years to go in his PhD, so I hope we'll have more, we'll be able to milk this database good. And we would like to extend this analytic solution that is valid for constant k to a variable k, variable eddy viscosity, but for that we first need to scale the eddy viscosity in the hurricane profiles from the simulations. And yeah, thanks. I hope this was interesting for you, and I'm happy to take any questions. Thanks.
Great talk. Thank you. Always very insightful from my own work. Any questions?
Please.
Thank you for very good work. So I have a question, or like, if we want to simulate the mesoscale vortex, like the subvortex in the hurricane, or like a microscale, like the tornado or downburst, what's your suggestion to get the control equation from this simplified MS stage? What's your suggestion for direction?
I mean, if you want to study subsystem within the bigger systems, then probably maybe this approach is. So it depends what triggers those subsystems, I think. For example, there are some oscillations in the outer layer of hurricanes that we cannot capture here. And we discovered that because at the beginning we were running simulation without stratification and an upper boundary condition that was probably suboptimal, and we were never matching simulation results. then applying stable stratification, we kind of killed that strange instability. I think in your case, if you were to run a very big domain and you have the mechanisms that support the formation of these secondary systems, then this approach could work. You just have to make it very large. But if you're missing those triggers, then this may not be sufficient. It's hard to say a priori. This is very idealized. I mean, hurricanes are not even axisymmetric, so we're making very strong assumptions. But yeah, it's a starting point, I guess.
Thank you, Professor, for your presentation. I wanted to know, when you were modeling far away from the eye, right?
Yes.
So, and then it's kind of, in a way, our inputs are linearized, in a way, because we're taking, it's completely in a log layer or the relationship. But as you get further into it, that kind of starts becoming, so do you have an idea at what radius the formulations we can take from this idea beyond it would not work? And it's
Yeah, I think it depends on from hurricane to hurricane, probably. That's something that could be scaled again in some dimensionless form, I would imagine. We cannot get too close to the eye, then the assumption of even zero subsidence breakdown. So this is good if you're a bit away from the eye wall, unfortunately, because we would like to be able to get there. But we ran some simulation with R equal 40, so it's 40 kilometers from the eye, and the eye wall I think was at 20. So it's a factor of 2, and I believe we have a validation for that, which looked okay. But yeah, it's hard to say if it's going to work all the time because there's a lot of parameters in the game.
I also I think while you're doing the computational grid, I mean, the process the schemes you use, is that you developed it in-house and it's your
We have a large eddy simulation in our community that has been developed by John Alberson, who was a professor at Cornell. When he was a student of my advisor Mark Parlange in 1992 or 62, very long time ago. That code, as we know every single line of it, and so we typically take bits and pieces to then develop other codes. We now have a code also in Julia that we developed from scratch that is very good for doing these kind of things. But yeah, it was pseudospectral codes are really good because you're using Fourier basis function in the horizontal. You have no dispersion error, no dissipation. Everything gets very clean for this type of simple domain simulations. If you want the code, I'm happy to share it. It doesn't have a manual. So historically, we just in the first year you hire a PhD student. The first year is telling the senior student teach the junior student. Now we also have actually, but now we fixed that. So if you want the Fortran code that has been used for this, I can share it with all the terms. I'm very happy to do that. The simulations that we ran are also uploaded in Design Safe CI. In fact, this is. So if you look for these hurricane boundary layer flow simulations in Design Safe CI, you can access to all those profiles. There is another code called boundary layer dynamics.jl that's written in Julia and is also pseudospectral mixed finite differences. That doesn't have hurricane boundary layer terms, but it's probably easy to implement them. And that has a manual. Like one of my postdocs spent 2 years just writing the manual for that code.
Thank you so much. So just one more.
Yeah,
I'm so
please.
sorry. So we've been working, I really here work with tornadoes. So, but we work with, we're taking, as the professor said, we work with subvortices and subvortices. So what do you, you said input parameterization and using data. So could a solution be using our experimental data to get our input curves that we could plug into our LES frameworks that could give us better parameterization?
Yeah, I mean, I would imagine if you have data for validation, then it's always good to then either improve a model or validate it and inform developments of closure models. I don't know if I would have to think about using this for a tornado, because then you're very small in scale. And but this code, this pseudo-spectral code, because it has very low errors, I mean, I would imagine you could generate a tornado inside the box.
Yeah, that's basically what it's a lot of for.
Because that would be pretty cool. I mean, I believe people already do that. I looked in detail, but
That's it. Thank you. Thank you so
yeah,
much.
thank you.
Okay, so I'm basically a freshman. I'm really looking forward to go to the PhD because the research is amazing. It's more specific a question, maybe a little dumb, but for example, if I want to go to Columbia to study civil engineering, in this case, the more concerned to wind, what should I prepare here? What should I do in research? Should I publish something? It just generally, like, not like I want to, for example, specifically study in Columbia.
Yes.
So-
Yeah, this is a longer. I mean, I can answer. Could take 3 hours to answer the question. But, I think nowadays it has become quite common to see undergrads with publications, and back in the past it was not the case, at least not in Europe. So I think having high GPA publication, one publication, maybe doesn't need to be in a top-notch journal, but showing that you know the process and some research experience. I think the summer research experience is very important.
Because I know that, I'm sorry to interrupt. Some of the, at least I saw that some of the Columbia University provides with the summer internships in
Yes,
the labs.
yes.
It's
You
going
can
to
apply to summer SURE program. It's an Amazon-sponsored summer program for undergrads from other institutions.
What's
You
it
get
called?
SURE, S-U-R-E. Sponsored by Amazon, my employees. Advertise it that way. There are also others, REU opportunities. Yeah.
Because I'm not like to be honest, I'm not civil engineering. I'm actually geophysical.
Yeah.
Yeah, that's why. But
I think in these, when you go to research, it doesn't matter if you're civil, mechanical, just science, applied math. Kind of all gets together a bit. Like the engineers become a bit more mathematicians, the physicists become a bit more engineers.
Yeah.
At least that's my.
Geologist becomes
Thank you for the questions. They're very, very good.
So I am an atmospheric scientist, mainly working on synoptic scale processes. So I'm just curious, because I'm not so familiar with large engine simulations, but I'm aware that there are already some existing models addressing this specific problem for the war. I think Giometto has a version for large engine simulations as well. So what's the biggest difference between your model and the existing models?
Okay, yeah, that's a very good, very good question. I think models like WRF, they've been developed over many years to tackle very realistic flow scenarios, and they're really optimized for a wide range of applications. In this case, these models, they're very narrow focused. Like if I want to add radiation to this, I would have to implement it myself. It's not in there. So this is like the kind of a bare bone code that does just that. In our code, we've been doing a lot of that, and we've been sometimes criticized for that. But it's a problem. We want to keep it very simple, and then try to do a bit of fundamental research. Then, of course, the applicability may be limited. But it depends what you want to do. Like for me, I like to stay between fluid dynamics and geosciences. So I want the theoretical part to be very heavy, and I cannot go very heavy if I tackle a problem that's too complex. So this one is simple enough. I mean, this code is very narrow. We do flow over urban environments, flow plant canopies, air-sea interaction now, but it's all within this open channel flow setup, which is well tested and validated. We're developing other codes that are a bit more generalizable. But yeah, this one is very. That's I think the main difference. You could use WRF to tackle this problem, but then you're giving up, for example, the pseudospectral accuracy. I don't know what the impact of that might be, because WRF has finite differences. I think approach high order, but still finite differences. And I don't know about the speed. This is really faster and optimized. I believe WRF is also.
Yeah, it can
but-
be costly if you to really high
Hmm?
resolution. It can be costly if you go to really high resolution. Your domain size is large.
Also, this code, I know every single line of it. Literally, I rewrote
Yeah.
every single line.
Yeah.
So, if something goes wrong, I know exactly what might be happening. A code like WRF, I don't know if you can get that level of control. Like a student in my group, usually after 2 months, knows the code inside out. 2-3 months. Because it's a very compact code, it just does what is needed for that precise task. Yeah, I mean, it's still solving PDE, so it's not that simple, but yeah.
Thank you.
Can I again ask
Yeah,
a
yeah.
question? It's more about geophysical. I'm sorry, I was a little bit late. I didn't hear how did you get the database? Because is it the same as remote sensing, or you use?
No, we generated it via numerical simulations,
Ah.
3D numerical large eddy simulations.
And it's because, I actually also trying to do the same, but not in this field. But thank you so much. So we did simulate.
Okay, we have time for one last question. Any other very good questions? Jacob?
I had a quick question.
Yeah.
How did the heat fluxes behave in your simulations? I'm just curious.
So, yeah, I know the heat fluxes in hurricanes are very important, but in this case, the background stratification, we used it mostly as a nudge term. So we wanted the flow to be stably stratified, because otherwise we cannot get the right behavior in the outer layer. If we initially we thought, okay, in a hurricane the wind speed is so high, and that stratification should not matter, but actually we figured it does matter quite a bit away from the wall. And so what we do is we fix the temperature profile that's based on empirical evidence, basically what the gradients are, and then we add a nudge term to that equation that keeps it there. So thermal part is just adding buoyancy
Just like
to
a
stabilize
prescription.
it.
Yeah. Thanks.
And this was an idea of George Bry, so we copied that idea. It worked well. All right,
So-
thanks for the many questions.
Yeah. So let's thank Dr.